Hello, get ready with a bunch of scratch paper and a calculator. When you calculate the non-standard Gibbs free energy change for chemical reactions, the calculations can be quite hairy. So I'll take it through it slow, and you might have to do this several times to build up your mastery for this, okay? So first of all, we've talked about the standard Gibbs energy. We know that it relates enthalpy, entropy, and temperature to the free energy change for the chemical reaction. And normally we calculate the enthalpy and the entropy at standard states. So that's why we have the little circles there, right? Standard state means 1 atmosphere whenever you're dealing with gases. It means that you have 1 molar solution whenever you're dealing with solutes. And it means that the temperature is 25 degrees Celsius. But that's highly unlikely. I mean, how many times do we do a reaction exactly at 1 molar and 1 atmosphere pressure and exactly at this temperature? That's a pretty warm temperature too. So, our lab isn't set up to do this. The temperature fluctuates and so on. So this is where we have the non-standard Gibbs energy. All right, so we know, as usual, delta G is equal to all of that. But now we throw in a twist, all right? And here's the twist, and you want to write this equation down. Delta G, notice how there's no circle there, okay, as usual, is equal to delta G with a little circle there, okay? So it's equal to the standard Gibbs free energy change plus this new term, RT ln Q, okay? Now, delta G standard comes from the calculation of delta H minus T delta S, where the temperature is 298 Kelvin, which is standard state. Okay, R is 8.314 joules per mole per Kelvin, and temperature is whatever temperature of the chemical reaction that you're looking at. And ln means natural log, and Q is the reaction quotient, right? We saw that when we were talking about equilibrium. It's the concentration of products divided by the concentration of reactants. So let me take you through an example from start to finish, and you'll see how this works. There are several different steps in this calculation. So it looks like an ammonia synthesis reaction. We've got nitrogen gas reacting with hydrogen gas in equilibrium with ammonia gas. And we have these different molarities of gases, and we know the temperature is 50 degrees Celsius. I don't even know if this reaction is at equilibrium. I don't know if this reaction is going to the right or to the left, or what's the energy change, okay? So we want to calculate the non-standard Gibbs free energy change for this reaction going from left to right under these particular conditions. So first we want to calculate the delta H, and I did that before in a different video. Step 2 would be to calculate the delta S. I also did this in a different video. Okay, I'm just going to skip to this point because there would be too much to show you if I took you through all those steps, okay? But you want to do all this calculation, and then you want to calculate the standard Gibbs free energy change, okay? The delta G with a little circle there means standard Gibbs free energy change, and that's delta H minus T delta S, but you use 298 Kelvin, which is the standard temperature, and that value is minus 33.0 kilojoules per mole. I'm going to write that up down on the upper left of this slide so you can have it for reference, okay? So that's, the first 3 steps there. We kind of blasted through it. We've done that. We know how to do that. This should be a little bit of review, okay? Now, this is the new stuff. Now you want to calculate Q. We've done this before with other chemical reactions, and it's products over reactants. So ammonia is the product, so it's NH3 squared because there's a 2 there, and that's divided by the reactants, which are on the left of the chemical reaction. We've got nitrogen, and then we got hydrogen cubed because we have a 3 in the balanced chemical equation. And then, as usual, you plug in these different concentrations, and you get a number on your calculator, 0.17. Remember that equilibria, constants, and Q are unitless. They have no units. So we're just going to write down in the upper left-hand corner of this slide, Q is equal to 0.17. Now, when you're doing thermodynamic calculations, you need to calculate all of the temperatures in Kelvin. So I've erased a lot of stuff off this slide, but I still have the temperature here. It's 50 degrees Celsius. So grab your calculator, add 273.15, round to the ones place. You get 323 Kelvin for this. I'm going to go ahead and place that on the upper left of this slide as well, so that you have reference to it, okay? Now we're going to calculate the non-standard Gibbs free energy change for this chemical reaction, but let's fix the R unit. Now remember, Gibbs is always kilojoules per mole, and the R constant is in joules per mole. So grab your calculator, divide by 1,000, and I'm just going to write it as 8.314 times 10 to the minus 3 kilojoules per mole per Kelvin, okay? And I'm also going to jot that down in the upper left corner of this slide so we have it for reference. Now that we have all of those little values all set up for surgery, so to speak, now we can go in and cut to the chase, so to speak, all right? So we have this non-standard Gibbs free energy change equation, all right? Delta G naught, which is the standard Gibbs free energy change, was minus 33, okay? We add RT ln Q. So I've got R, I've got the T, I've got the ln, which is the natural log, and then that's 0.17, okay? I'm not going to take you through the mathematical intricacies here of how to use your calculator, but I get minus 33, and then I'm going to add a negative 4.7, and so the value I get there is negative 37.8 kilojoules per mole as the final answer, okay? Let's go ahead and review all the different steps necessary to calculate this, all right? So first of all, here's a grandiose equation that you need to write down and know how to use. So the first step is usually to calculate the delta H for your reaction, calculate delta S for your chemical reaction, then calculate the standard Gibbs free energy change, and this is where you want to plug in that 298 Kelvin in place of temperature here, okay? And that's how you get the delta G with a little circle there, okay? Now that you have that, you can calculate Q. Q is products over reactants, as usual, right? And then you can use the equation, okay, at the top of this slide. Delta G is equal to delta G naught plus RT ln Q. And the temperature you want to use in this equation is the temperature from your word problem. It might be 400 Kelvin or, you know, some crazy condition, or even negative 200 degrees Celsius or something. So, you know, plug in all those temperatures as appropriate, okay? Also, write this constant down. R is equal to 8.314 joules per mole per Kelvin. Just remember, when you use it in thermochemistry here, you want to divide by 1,000 so that you have kilojoules, kilojoules, kilojoules everywhere, okay? I know that was a lot. I'm sure you'll have to slow down and carefully review this and do some practice problems of your own. But please like, please subscribe, and have a great day, everybody.